What's going on, everybody? It's Mr. Gustin. I am not in the physics classroom. I'm in a physics room, but not the physics classroom. So anyway, I wanted to do a Unit 1a kind of review for all of you that I think should be helpful. And so that's what we're going to do. I'm going to talk about where we started this year, where we went, and the things that we should be aware of, labs and whatnot for our Unit 1a test. So where did we start? We started over here. I'm going to slide this way. We started with this very basic idea that Newton's first law states objects in motion remain in motion and objects at rest will remain at rest. And we gave one giant caveat, and that caveat is unless they are acted upon by an outside and unbalanced net force. And this was the basis of everything and is the basis of everything we've done this unit. We started with our buggy. We started with our ball on the ramp. We went to the bleachers and dropped some stuff. And every single time we asked ourselves the question, was an object accelerating or was it moving at a constant velocity? And our answer was always rooted in Newton's first law. Was there an unbalanced force or were there balanced forces? If there were balanced forces, we knew it was moving at a constant velocity. And if there were unbalanced forces, we knew the object was accelerating. Let's take these first three examples. The dune buggy was the very first thing that we did. And we labeled some things. We brainstormed some forces. We said, hey, there's a force of gravity acting on the dune buggy. We said there's got to be some kind of propulsion force. Let's call it F motor, pushing that buggy forward. And then we looked at the buggy and said, well, it's moving at a constant velocity. So if it's moving at a constant velocity, and Newton's first law is a law of nature, there must be some kind of resisting force or balancing force. So we said this was a force of friction of sorts from perhaps the axles, but these two forces were balanced because the dune buggy was moving at a constant velocity. We also said there must be some kind of balanced force holding up the buggy because gravity wasn't accelerating it down. So this was the force diagram we came up with. There were balanced forces. This allows us to explain why the dune buggy is moving at a constant speed. We then went to the ramp outside, or not outside, the ramp down near the lower glass comments, and as we rolled this ball down the ramp, we saw that this ball started from rest and sped up. So there must have been some kind of gravity pulling it down the ramp, some kind of force pulling it down the ramp. And so we looked at these forces and said there were in fact unbalanced forces, an unbalanced force, gravity down the ramp, and then the surface pushing back on the ball. And one of these forces, probably gravity, was responsible for accelerating the ball down the ramp. So we saw constant velocity with balanced forces. We saw a constant acceleration with unbalanced forces. And the last example we have is going out to the bleachers. And on the bleachers, we went ahead and dropped some objects. And in this case, the only force acting on it was the force of gravity. We gave that a special name. We said that object is in free fall. And we then also said, hey, that object must be accelerating constantly. So we made this distinction early on between objects moving at a constant velocity and objects moving with a constant acceleration. All of this was based on Newton's first law. And then we studied some things further, and we said, let's not just worry about whether or not they're accelerating. Let's worry about whether they're speeding up or slowing down. Let's examine the differences between speed or velocity and acceleration. So we tried some weird things. We said, all right, let's start with the object on the ramp like we had before. We've got an object on the ramp, and its initial velocity was 0 meters per second. And here were the forces. There was a force of gravity, and there was a force from the surface. And I know that at the end, the velocity final was equal to something that was bigger than 0. So this thing was going down the ramp. It was speeding up down the ramp. And we said that, okay, the motion was this way. This is the direction of motion. And the direction of acceleration was down the ramp. And we said when the object is moving in the same way that it's accelerating, we said that that was in fact speeding up. And then we tried something different. We said, okay, what if I took an object with the same force diagram and I rolled it up the ramp and its motion was up the ramp, but that gravity force, some part of that gravity force was holding the ball back or was pulling it back down the ramp. So my motion was up the ramp, but my acceleration was down the ramp, if these two things are pointed in opposite directions, we called this slowing down. So it wasn't necessarily an acceleration and deceleration. It was how is the acceleration or change in velocity related to velocity, the motion. If they're pointed together, we see a speeding up. And if they're pointed in the opposite direction, we see them slowing down. And this required us to kind of come up with a strong definition for the differences between velocity and acceleration. So when it turns out that velocity is simply, in words, it's the change in an object's position or location, let's call it x, over time. How quickly is something moving to a new location per second? Mathematically, we said that velocity is equal to change in position over time. That's a mathematical expression we could use. Acceleration was different, though. Acceleration was not necessarily change in position over time. Acceleration was the change in velocity, or v, over time. So acceleration is equal to change in velocity over time. Now, both of these things are very, very similar, but they're still different. And a lot of high school physics students, for some reason, get these things confused. Velocity is simply telling me, it's the one I'm most familiar with, velocity is telling me where my location is and how quickly that location is changing per second. Acceleration is telling me how quickly that rate is changing. So if something is going to speed up or slow down or change velocity, it's the result of an outside unbalanced net force that causes an acceleration, and that acceleration, if I bring this thing full circle, acceleration causes that change in velocity, or the change in a rate of position over time. This is the definition. This is one of the most complex questions that students struggle with early on in kinematics. The differences between velocity and acceleration. Acceleration is a change in velocity, and velocity is a change in position, both over time. These were the big ideas that we took away as we introduced physics to you. The next thing we did was we took this motion and said, what would it look like if I sketched these things on graphs? So we did that. Let's do that now as examples. For the first example up here, I'm going to do it in blue to differentiate a little bit. But we went ahead and said, let's look at this graph right here. Let's sketch the position and time graph and a velocity and time graph for the object as it rolls down the ramp. Well, we had to think of a few things. All right, the first thing we thought of is what's the initial velocity of this object to sketch this position time graph out. So we did that. We said, okay, the initial velocity, it starts from rest. Let's sketch that. This thing moves down the ramp. I'm a fan of calling most things positive. So we said if it moves down the ramp, the velocity over time as time moves on is going to get more and more positive, but it undergoes a constant change. So I see a linear velocity and time graph. There was a constant change in velocity because there was a constant unbalanced force, which results in a constant acceleration or a constant rate of change of velocity. So I see this VT graph right here. When I come back to think about sketching my position and time graph, the position and time graph is weird because my velocity is changing over time. So if velocity is changing, then my position over time is changing. And in fact, position over time, that's the slope of this graph right here, right? I'm sorry. The slope of my position in time graph tells me this. The slope of my position in time graph tells me velocity. So if the velocity is very, very big, I would have a really steep slope over here on my position time graph. If the velocity is at any instant very, very small or close to zero, I'd have a very small or close to zero slope on my position and time graph. The slope, position over time, is velocity. So what I do is I like to look at my velocity and time graph and say, okay, initially, what is my velocity? So initially, if I look at my velocity, that initial velocity, it is 0, which means the slope of my velocity, the slope of my position in time graph should be 0 initially. So I go ahead and I make the initial slope 0. It's hard to see, but I make an initial slope at the beginning of my position time graph, I make that 0. As time goes on, the velocity becomes very, very, very positive. So my slope later on at that same time is going to be very, very, very positive. And instead of playing connect the dots like my daughter or my nieces and nephews, I want to play connect the slopes. This is an advanced class. We play connect the slopes here, not connect the dots. So I connect my very, very 0 slope to my rather positive slope, and I end up with an upward opening parabola like this. And for those of us that have done many labs where I've gathered position and time data for an accelerating object, we know that position and time graphs should follow some kind of quadratic pattern when we see constant acceleration. So these are my two position and time graph and velocity and time graph sketches here for an object as it rolls down the ramp. Now, if I wanted to sketch an acceleration in time graph, acceleration is simply the slope of my VT graph. It's velocity over time. If I'm looking at a VT graph, it's velocity over time. So I simply look at my VT graph and say, what's the slope there? I look at the slope. It's a positive number, so there's my acceleration in time graph. Just a positive constant line because this is a positive and constant slope. A second example we can do rather quickly is the object as it rolls up the ramp. Let's do position in time, let's do velocity in time, and let's do acceleration in time. Now, what I do know is that as this thing rolls up the ramp, the acceleration is down the ramp, so I have to choose which direction is positive, which direction is negative. I'm going to say up the ramp is positive, down the ramp is negative. Very simply put, my acceleration is constant and it's down the ramp, so I'm going to go ahead and go boom. Acceleration is now constant and negative as the ball rolls up the ramp and comes to a stop. End of story. All right? If I look at my picture, though, and I know the motion is up the ramp to a point when the object stops, I want to think about my picture, and drawing a picture is an excellent way to help you with the graph. So the object is moving up the ramp, and because you and I have existed in this world, we've played with objects, we've rolled things up hills, we know that as objects roll up hills, eventually they come to a stop. So I know when I'm thinking about this, if the ball is rolling up the ramp in the positive direction, it's going to have a positive, very positive initial velocity. As it rolls up the ramp, at some point it's going to stop. And when it does stop, that velocity is 0. So I see myself here having a constant, negatively sloping velocity time graph that ends when velocity is 0. I can double check my acceleration graph now. I can say, hey, is this slope of the VT graph, which is acceleration, is this slope constant and negative? Because that's what my AT graph is. And if it checks out, if they match, wonderful. Going to the position in time graph now, I want to kind of follow the same pattern I followed last time, right? The velocity tells me the slope of this graph. So if I look at, I don't know if you just heard that. I'm in the office or in a room recording. Someone just like got knocked into a wall. So if that loud noise interrupted you, it interrupted me. Someone just like fell over in the hallway. So, all right, we're back. We're good. The child was fine. All good. Where was I? We were talking about our velocity time graph and acceleration time graph for an object as it rolls up the ramp and slows down to a stop. We said the velocity time graph matches my AT graph. It's a negative slope up here, so it's a negative acceleration down here. We said it goes from a very positive velocity to a very 0 velocity because it goes up and stops. We're looking at our position time graph. So I want to use my VT graph to examine my position time graph. So here's the deal. My velocity tells me the slope. So the velocity initially is very, very positive, which means I want it to have a rather positive slope. But it's a positive slope moving forward. So I'm going to see a very, very positive slope to begin with. So that's my very positive slope right there. And as time goes on, velocity gets closer and closer to 0. So as time goes on, my slope, as it moves forward in the positive direction, should get closer and closer to 0. And so again, this is an advanced class. We don't play connect the dots. We play connect the slopes. So I go very positive to 0, This is my position and time graph for an object as it rolls up the ramp, okay? These are two rather basic examples. We saw things get far more complicated. We saw things talk about going from words into then graphs and translating between graphs. But the big ideas can be boiled down to this. If I take these big ideas of connecting velocity, acceleration, and position graphs, it can be broken down into these three major sections: a position and time graph, a velocity and time graph, and an acceleration and time graph. Here are the ways I can interpret and translate between these things. Here are the notes we took. We basically said the slope of my position and time graph tells me the velocity. The slope of my VT graph tells me acceleration and time. And folks, I'm leaving this up here because it's the stinking definition, right? Like the slope, position over time, is velocity. That's the slope. This is mathematical, this is graphical. The slope of my velocity time graph is acceleration, folks. It's the stinking definition. Velocity over time is acceleration. The crazy thing that we also noticed was if we take the area, if we take the slopes, we move forward in our graphs. If we take the areas, though, we move backward. And what I mean by that is the area, if I've got an acceleration curve that looks like this, I can take the area of that curve, and the area of that curve will tell me the change in velocity over here. It moves me back. It doesn't tell me the initial velocity or the final velocity, but it will tell me the change in velocity if I take that area. If I take the area of, say, a VT graph, though, the area moves me back, and it will tell me literally the change in position. It won't tell me initial position. It won't tell me final position, but it will tell me exactly what my change in position or displacement was over here. So moving forward, slope of position time, that's velocity. Slope of velocity and time, that's acceleration. But moving backward, I see that the area of my AT graph is changing velocity, and I see that the area of my VT graph is position. But check out this mind just boom, explosion. If I were to rewrite these equations, say I multiply both sides here by time, check out what happens. I get V times T equals change in position. Dudes, V times T, area multiplying, tells me that graphically and mathematically I see the connection over here as well. If I multiply both sides by T, my T's cancel out, I get change in velocity is equal to acceleration times time. Folks, area, time, it's the same thing. I can get my mathematical expression here. I can get my graphical expression here. I'm hitting both of those standards, trying to make the connections between graphing and mathing right here to hopefully make translating between my kinematic graphs much easier. Now, on an assessment, will I give you something this easy? Maybe, if I'm feeling nice, right? Maybe this is a great kind of like where you at question, a great differentiating question. Can things get harder than this? They certainly can, and you saw that in our practice over the course of the unit. You can go back and look at those practices and the keys that we have for those, or the discussions we had in class if you want more challenging translating between graph questions. After all of this graphing, we said it's finally time to start hammering home with some equations. We looked at some various scenarios in our labs. And the first lab we did that with was our Speedy Lab. The Speedy Lab was kind of the first place that we got some mathematical equations from. And if you remember the Speedy Lab had two parts. The Speedy Lab has two parts with a dune buggy as it moved across the floor at a constant velocity. And it was the ball as it rolled down the ramp. We've already talked about their force diagrams, whether they accelerated or not, but I want to talk about the data. Because with the constant velocity data, we took position and time data, and we generated a graph like we would in any lab. With any lab we generate graphs, we linearize these graphs, and we go ahead and create equations. Once we did this, the constant velocity, we saw position and time for the dune buggy. This slope was constant. And again, if you could pause the video right now and remind yourself what is the slope of the position time graph, you would say to yourself, velocity. Mr. Gustin just said it was velocity, and you'd be right. So the equation that we come up with from this graph ends up being that position at any time is equal to the velocity, which is the slope, times the time of the object as it moves, plus whatever the initial position is. This was the first equation we came up with, and we said that this equation is fantastic for objects that move in constant velocities. This was the first equation we had. It only works for constant velocity. Notice it doesn't have an acceleration term. Velocity can't change because it's one velocity, and the only thing that's changing is position. All right, from this we could write ourselves a proportionality statement. We could say that for objects in constant velocity, we might say that that time is directly related to position. But again, this is only for constant velocity. The very rare case that objects move at constant velocity, these two models hold true. Now, we then went and moved this thing and rolled it down a ramp and took the exact same data. It was position and time data. And for the first time, we saw this weird quadratic function. We're like, well, that's not a line. I can't write an equation from a quadratic. We only can write equations from lines because otherwise there's too many variables and unknowns, and I got to take an ax and the bx and the time squared, and it doesn't make any sense. So we had to linearize. And linearizing is understanding what the shape of the graph is telling me, calculating or editing or massaging my data to figure out a linear relationship. And so we did that. We said this thing looks quadratic, so maybe we should linearize by taking t squared. And we did that. And when we did t squared, we got our linear function. And we said this means that position is related to time squared. That's not an equation, that's a relationship. That as x goes up 5 times, t squared goes up 5 times. This was a mathematical relationship, a proportional relationship. Eventually, not in this lab, but eventually we came across the quadratic. Eventually we assigned variables to the entire quadratic function, and we came up with this equation, that x is equal to the initial position plus the initial velocity times time plus 1/2 at squared. This equation comes from the relationship between position and time squared. I'm going to use this equation if I'm looking for a position and I know time squared, or I know position and I'm trying to find time. This is a great equation to use if that is the information I have or I am given. This was an equation for position and time for objects undergoing constant acceleration. Earlier, we talked about the difference between velocity and acceleration. Velocity is change in position over time, and acceleration is a change in that velocity. So, if objects are showing a changing velocity, this is the mathematical model I want to use. And if objects are not showing a change in velocity, this is the mathematical model I want to use. I also came up with eventually 2 more equations from data and from research. I came up with this equation. Velocity and time. That was in fact linear, so the equation I got from this was velocity equals acceleration times time plus initial velocity. And the relationship here is velocity is related to time. This again is for objects undergoing constant acceleration. And then the last equation that I got came from a velocity squared and position graph. And that tells me that v squared is equal to v initial squared plus 2a, I prefer to say change in position, and that v squared is related to position. Again, only for objects undergoing constant acceleration. If objects are not showing a change in velocity, this equation holds true. If objects show a change in velocity, these 3 equations hold true. These were the big equations we came up with. We worked through how to use them, when to select them. My biggest thing is when I'm looking to select an equation, I'm trying to figure out, well, what are the 2 variables being related here? This is position and time, this is velocity and time, this is velocity and position. Draw your picture, figure out what it is you need to know, and then go ahead and select the appropriate equation. These are also the graphs from data that match them, and hopefully if you can analyze those graphs, you can also interpret what their slopes are, because they're not all acceleration. If you forget about that, head back into your labs and examine those labs. What are those slopes trying to tell me? Okay. The last lab we did, was our free fall lab, was our G-Whiz lab. We turned things and moved them vertically. And what we found was that the motion of vertical objects is simply put, it is constant acceleration motion. It's not constant velocity. Objects that are dropped from rest or dropped in general, like the back of the bleachers, undergo constant acceleration. That acceleration we called baby G, and we said that was 9.8 meters per second squared downward. That objects will accelerate towards the Earth at that rate. We talked about how these three equations all still work, but we might change their variables from x position to y position to indicate a vertical drop instead of a horizontal drop. But generally speaking, folks, these were the major concepts. The graphs, translating between the graphs and our thought process about that. The data graphs and linearizing those data graphs, creating equations from those data graphs, interpreting slopes from those data graphs, and then identifying whether or not an object is undergoing constant acceleration or constant velocity, how to determine the difference between the two, and what is the difference between constant acceleration and constant velocity. Those are the big ideas. The big ideas can be summarized by Newton's first law, that objects will stay in motion unless acted upon by an outside unbalanced force, or objects will stay at rest unless acted upon by an outside force. Basically, outside unbalanced forces cause changes in motion. Changes in motion can be described as having accelerations. That could be speeding up if the velocity and acceleration are pointed in the same direction. That could be slowing down if objects' velocity and acceleration are pointed in opposite directions. And hang on to your hats, folks. If they are pointed perpendicular, it's not speeding up or slowing down. It's a change in direction. But we'll come back to that at a later unit. Okay? Good luck on your test coming up. For now, study this. Look at the old YouTube videos if you want any of these things broken down a little bit more. If you've got questions, feel free to come see me, email me, those kinds of things. But you have the resources that you need in order to be successful, and I know you'll be successful. Okay? Until then, see ya!